Hey guys, all right. So can we hear me okay if I'm back here? Final mic check before we get started.
Yeah, sounds good.
Okay, sounds good. If I get too quiet, y'all just remind me. I want to make sure you can hear me from on mic. So a little bit of background on me before we get started. This is workshop one in a series of physics workshops. I myself am a PCC student, just like you guys. I've been here for about 2 years now. I study physics and I also tutor physics here in the NatSci STEM Center. I've been tutoring for a little over a year in physics, and then I also tutor high school students in science and math. So what I'm trying to do is bring you guys a little bit of the student's perspective. When you're in your physics courses, you're going to have your professor teaching you physics. He or she will be showing you guys a lot of things. But I wanted to try to, at least with this first workshop, give you guys some tips and tools for what a student can do to most efficiently and effectively study physics. The way that I actually worked this workshop up is I sat down with my friend Victor. He's a fellow physics student, and we started talking about what were the number one things that we wish we would have been shown right as we started to learn physics. So the workshop that we're going to do today is what kind of came out of that, and we're just going to be focusing on how you guys can effectively study. So we're going to do strategies for students beginning to learn physics, how to absorb your concepts, how to organize your notes, and how to understand your equations. And this is super central. This is super central to physics because a major stumbling block in physics are the formulas and equations. They're at the heart of physics. In fact, the power of physics is all tied up in what we can describe mathematically with equations. But we've discovered quite a bit of physics since we've been doing it for almost 300 years. And there are dozens and dozens of equations. In fact, in your very first physics course, you'll learn dozens of equations. So the question is, how can you efficiently organize them and utilize them? And it's a two-sided thing. You need to be able to bring up those equations either from memory or from your notes. And you also need to know when and where to apply them. And what that requires fundamentally is a really intricate understanding, a deep understanding of those equations themselves. That's what we're going to go over today. I'm kind of going to try to give you guys some practice on how to read and understand equations. That's what we're going to start out with. So let's look at part one, reading and understanding formulas. This is, I think, stumbling block number one. I get students a lot of the time who will come in and say, oh, I'm not good at math, or I don't understand this, or I can't read this, etc. when they're talking about physics. And I think that comes from an expectation that reading and understanding math is going to be like reading and understanding English. So those of you who've been reading or writing English for a while, I'm willing to bet I've got some words right here, right? I've written part one, reading and understanding formulas. When you looked at that, you didn't really have any trouble understanding it or reading it, right? You pretty much processed that instantaneously. Understanding is a pretty involved word. It's got several letters, but I don't think you struggled and you had to sound it out or read it bit by bit. Now, students often come with the expectation that when they're reading their equations, it's going to be the same thing. But if you remember when you were first learning to read, maybe you were 6 or 7, you came to a word like understanding, and I don't know that word. I haven't memorized that word. I haven't recognized that word. And what would your parents or your teacher tell you? They would say, sound it out, right? And when you go bit by bit. You go understand, understanding, right? And we sound it out. And you build up that familiarity until eventually you can sight read that word. And you do know it instantly. But as a physics student and going through your career with mathematics, whatever you're doing in STEM, don't expect yourself to instantly understand something. So when I flip to the next page in a second, and we see some equations on it, give yourself some time and go through it bit by bit. Read it slowly like we're sounding it out from the words. That's going to be our approach with everything. It's very easy to see a page full of math and just go, I don't know what that means. I still do that. I'm not going to instantly be able to read it until I work my way across the page and I go through each symbol. So let's look at that. So we're understanding formulas. You want to say it in words, and you want to say it in math. So up here we have VF equals VIT plus AT. What does that mean? When you guys encounter your equations in your class, and remember how I said there'll be dozens of them, right? Your professor is going to be handing you equations every couple minutes. You're going to have a lot to track. Make sure that you write down and make sure that you understand what each symbol means. Each symbol, each letter. So let's go through it one by one. VF is final velocity. Final velocity equals initial velocity plus acceleration times time, or multiplied by time. When we put it in words and we say it with math, that is the same thing as like for reading, sounding it out. And when we understand each symbol individually, we can understand the equation. And we can break down that barrier where an equation looks complex. It looks like we can't understand it. If you just take it bit by bit, you'll start to develop your understanding, all right? So we're going to go over first to exercise 1 on the worksheet. I'll pull that up on my screen here. We're going to go through a couple of examples from exercise 1A. So for each of the below, try to convert the relationship described into an equation. The first one, I, is the distance is equal to the rate times the time. So we read that out. And then my question to you is, can you convert that into the symbolic language, the syntax of math, the shortcut analytic language that's easy to handle, but not always the most easy to sight read or understand? So for those of you guys online, I think, do they have the link to the worksheet? Okay. So maybe I can send that to you over, and then we can work on that at home. Yeah, let me share it with you real quick. I share that to you in Discord or in the Zoom, maybe. All right, one brief second, guys, as I send this over. Okay. Sorry, I wasn't in the Zoom. I'm going to join into it. All right, so I've sent that link to you guys there. Let's continue on. So the distance is equal to the rate times the time. For those of you guys that are online, I think I'll go through a couple of the examples here in person, and then I will encourage you to work through the rest of them on your own, and I'll give you some time to do that. So the first one, number I, right here. The distance. We pick a symbol for distance, okay? Let's choose D. It's both the most common and it just makes sense. D for distance. The distance is equal. So D equals the rate times the time. What do you want to call rate? Let's just put an R. Rate times time. That's R times T, or just RT. D equals RT. Go through the rest of the list here. Force is equal to mass times acceleration. See if you can write that one out. See if you can write that one out. Density is defined as mass per unit volume. For each one of these, pick a symbol, pick some language so that you can understand, and then relate these variables, right? What are the variables? Density, mass, volume. The velocity at time t is the derivative of the position at time t. That one's a little bit trickier. So I'm going to move on, and then we'll come back to these, and we'll kind of go over some of the answers after you've had a little bit of time to work on it. The flip side of that, you said say it in math, say it in words, right? So now let's do the reverse, right? And this is more common. Your professor is going to write the short way more often than not. They're not going to write the whole thing out on the board. So you really want to be able to translate mathematical shorthand into words for your notes and for your memory so you can understand. R equals D over T, or D divided by T. A of T is equal to V prime of T. How would we say that one in words? V prime is the derivative, right? Delta X is equal to V sub 0 of T plus 1/2 AT squared. Go through the list and we'll put words to these. And I'll go back to them and we'll go over the answers. So I'll give you guys a second to go to that sheet, write down what you think that you would say. See, but online,
This meeting is being recorded.
I don't think I can make it any more clear for you from here online. Those of you guys that are in the Zoom, can you see the slides okay or not so much?
Yeah, the slides is fine.
It's fine? Okay.
Mm-hmm.
All right. Good. Okay, so we made some progress through those exercises. If you didn't finish, no worries. I'm going to keep going, but later on when we have time, we'll go back over them. And you at home or you later on can have your worksheet and you can work through it at your own pace. Okay, so we've done our first pass. We did our first pass reading. We read the formula and we understood it both in words and we understood it symbolically. So we're ready now to do our second pass, and we want to understand the implications of the formula or the implications of the equation. I'll use those words interchangeably. This right here is the kinematic equation for position. If you haven't encountered this one in your physics course yet, you are certainly soon to encounter it. It's very core. You'll see it very often. It says xf is equal to xi plus vit plus 1/2 at squared. Now, just like we did before, let's read through it. Before we start doing the implications, let's read it through. xf, that's the final position. So x is some point, and x sub f is the final point, the final position. It has units of meters, so we're measuring it out in meters. X sub I is the initial position. That's measured out in meters as well. So far we have that the final position is equal to the initial position plus some stuff. That kind of makes sense, right? Where you end up depends on where you start, and then probably some other stuff. Let's see what other stuff. VI, we have the initial velocity. So your starting speed, right? Your starting speed. What does this say? This says your starting speed times the amount of time that you travel. A is for acceleration. The acceleration is how your speed is changing over time. So we start at some speed, we increase our speed or we decrease our speed. We do that for some amount of time. T is for time. What do we end up with? The final position, it depends on where you start. It depends on what speed you travel at and for how long you travel. And it depends on how your speed changes over time, right? That makes intuitive sense. Let's think a little bit deeper about some of the implications of this formula. We're going to do the same kind of by-parts approach. So let's answer some of these questions. What are the variables here in this equation? There's a lot of them present, right? There's a lot of things that can change. What is a variable? Something that can change, right? Something that can vary. What all in this equation could change? The main variable is time. We run everything as a function of time. But if you're talking about what could be a different value, what could change values, everything in here could change values. We could start at a different initial position. We could start with different speeds. We could run for different amounts of time. We could consider different amounts of acceleration. And all of that would result in different final positions. What are the constants? What are the constants? The only thing that is a constant in this equation is the thing that's not changing is A. A is not changing. And VI starts out at an initial value, and it doesn't change either. Okay, now, this is the part that is, to me, key to maximize our understanding of the given equation. We're going to interrogate it a little bit. That means we're just going to go through it bit by bit, and we're going to see if I change one thing, how does it affect the other things in the equation, in the formula. So my question to you guys is, how can we travel further? How can we travel further? How can we make XF large? You want to travel a further distance. Off the top of your head, what are some ways?
Oh, we can increase the initial
Sorry, what was that?
position. We could increase the initial position.
Yeah,
Or
completely. So if we want to go far, well, if we started out far already, then we're pretty much already there, right? So if XI is very high, then XF will probably be high as well, right? Okay, what are some other ways we can travel far? How else can we travel far?
we can also increase the amount of time that we're traveling by.
Sure.
increase
What if we travel for a long time? Let's say we're a car, we're driving. We travel for a long time. T gets large. If T gets large, then we start adding up a bunch of stuff. We add a lot to XF. It gets large as well. What else?
We could also increase our acceleration.
Right. We can increase our acceleration, and similarly, we can increase our initial velocity, right? If we start at a high speed, that would also make us travel further. Now, this equation is very simple because all we're doing is we're just adding stuff up, right? There's a little multiplication in there. There's a little bit of nuance to it. But fundamentally, it's pretty easy to think about what happens if one thing increases. Everything else, the XF, the resulting XF increases, right? We're just adding stuff up together. That won't always be the case. You have to take it in a case-by-case basis for your equations. But I really encourage you to go through this process of thinking about what happens if I change one thing in my equation. What does it do to the other things? Specifically, what does it do to this left-hand side, right? The left-hand side is usually where we put the thing we want to solve for. And that's always a very interesting question to ask. And the more times you ask it, the more you'll become familiar with the equation and the more intuition you'll develop about when to use it. Okay, so let's go over. Let's look at the second part of the worksheet. Go over this briefly. So the second exercise is just what I had in the second slide. We want to explore the implications of this kinematic motion equation and of other equations. You can do this for any equation, and I encourage you to do it. So this is similar to what we just did. We just walked through this. You can write it down at home for your reference later. Some other interesting questions that we could ask. When does a certain variable dominate? When does it become the most important thing in the equation? When does it determine most of xf on its own, right? So when does the initial velocity dominate, right? Can you think of a scenario in which the most important element for determining the final position is only the initial velocity? Tell me if you can think of a scenario. So we look at the math, right?
Mm-hmm.
If xi is 0, it's not really contributing.
Mm-hmm.
If vi is huge, if it's very large, then it dominates, right? And if t is quite small, then the t squared multiplying by the a term doesn't really have a chance to grow and significantly impact the final velocity. So the main factor in the final position, is the initial velocity. That was a little bit trickier. Look, when does A dominate? When does the acceleration dominate? Two instances. Obviously, if the acceleration is very large, then it's very impactful, right? It's a large number. It adds a lot to the equation. We divide it by a half, but if it's still very large, it's going to have a big impact on our final position, where we end up. But another way that A dominates is if time goes on for a long time, because we're squaring time. So time squared grows a lot faster than just time to the first power, right? One is linear, one is growing like this, the quadratic curve. And that makes perfect sense. We travel for a long time, accelerating a little bit. Eventually, after a long, long amount of time, it doesn't really matter how fast we started. It just matters how much our speed has been changing. And that's when it will dominate. And this is another way that you can interrogate your questions. You can think about when is one variable more significant than another. The final pass. Let me full screen this for you. We did our first pass. We did our second pass. The final pass on your equation is to check it for common sense. Do a sanity check, especially in the early levels of physics when you're doing things like mechanics. You have an intuitive concept of how the world works. You've been operating in it. You've seen cars drive. You've seen planes fly. You've seen balls be thrown in sports. You know how these things interact. So do a sanity check. Do a check for common sense. Let's do pressure. And the reason I bring this up too is, remember I talked about conjuring from your memory many different equations? There's going to be many times on tests and things like that where you're not quite sure if you remember the equation correctly. And this is when you're going to want to use this check. Does the equation make sense? So let's look at this one. I'm saying here pressure. I pull this out of my memory. What is the pressure equal to? I remember P, F, and A. The pressure is equal to the force multiplied by the area. Let's think about, does that make sense? Pressure is force times area. First, you guys tell me, what's your initial impression? Do you think that makes sense or no?
Yeah, I think that makes sense.
Okay, yeah, it seems kind of right? Like the force should be involved and the area should be involved for the pressure. Let's interrogate it, right? So this is the pressure. And we would say if the force increases, right, if F goes up, then the pressure would go up. Does that make sense? If I put more force, then they feel more pressure. I think that makes sense. That's true, right? If it's a very light force, then the pressure is very low, right? Okay, so it seems good. That F in there is seeming good. Let's look at A. Let's look at A. If the area goes up, then the pressure goes up. Does that make sense? So now I'm saying, if I take a force, let's imagine the force is 1 Newton. Or let's imagine the force is as much force as I can put with one finger, right? A small amount of force, say, and it's over a large area. Is that a lot of pressure? Or is that a little bit of pressure? If A is large, does the pressure get higher or does it go lower? What do you think?
If A is large, then the pressure is lower.
Then the pressure is what?
Is lower.
I agree. That's right. That's our intuition. So my equation here has got to be wrong, right? I must have misremembered it because it doesn't make sense. If the area increases, then the pressure increases. Then how would a knife work, right? If a knife put a force over a large area to cut something, it wouldn't be able to do it, right? You don't have a knife that's a giant block that has a large area so that when you apply a small force, it exerts a big pressure. That's not how knives work, right? A knife is a tiny area so that a small force can exert a big pressure. So what should this say? We reason it out. It should say that the pressure is equal to the force divided by the area. The force per unit area. If you put a big force, the pressure goes up. If you put a small area, the pressure goes up. So with common sense, we figured that one out. And I encourage you guys to always do your common sense check on equations that you write down and equations that you're presented with. And it also increases your intuition and familiarity. It's part of interrogating the equation. Okay, so that finishes us with part 1. Let's go briefly to the final exercise for this part. And then I'm going to just give you guys some tips on note-taking, and then I'll open it up to the floor for you guys for questions. So exercise 3, we're talking about the intuition. I'd like you guys to place a check mark next to the correct equation and an X mark next to the incorrect equation. So I'm telling you guys a bunch of relationships, and it's your job to tell me whether that, what I've written, is actually modeling reality, whether that's actually true. So let's look at the first one together. So the rate divided by the time is equal to the distance. Is that true? Is a speed divided by a time equal to a distance? What do you guys think?
No.
No, I don't think that makes sense, right? We said that your final position depended on the speed that you traveled at times the time that you traveled it for, right? And we think about it this way. This says, what does this say? This says, if the rate increases, the distance increases. That's true, right? If we go faster, then we travel further. Is that true?
Yes.
Yeah, that's true. But look at this t. Look at this t. This says, if t grows, what happens to d? It shrinks. If we travel for a longer time, we go less far? No, I don't think so. That's not how it works, right? And these things are, you don't know them instantly. If I just tell you this R over T equals D, you don't instantly know that it's wrong. But you can just ask a couple of questions and you can figure it out. And if you guys practice this as you go, as you're learning in your physics, this will save you on a test. I guarantee it. Many times it will save you. Because you'll have written down hastily, as you're trying to go through the problem, the wrong equation. And you just check it, like we did. It took us like a minute, and that will save us. So definitely do that. Always do your sanity check. Does it make sense? Does it make sense? I've got several more exercises along those lines. We'll do those later. You can work them in your own time, and we'll review them a little bit later on. But I want to get on now to the second part, which is, so we've understood the equation, right? Our professor gave us an equation. We read it. We considered its implications. And we also checked it for common sense. We checked it for common sense. Now, he keeps giving us more and more equations, and it's getting to be a lot. So we need to organize our notes, and we need to stay organized with our memory. Let's just do some tips for note-taking. Again, you guys will have your own style for note-taking. You'll develop that. But as I learned physics over the course of a year, I initially did my note-taking pretty bad, and I learned some things. And I think that if you guys start out, you'll be able to build a much stronger foundation than I initially had. So I do my notes on paper, but if I were to write them out online so that you guys could see them and you could read my handwriting and everything, this is how I would do it. So we're talking about Newton's second law. I write out what that law is. That's basic. You guys know that. But here, what's good about these notes right here, I box the formula and I make it easy to find. Because remember, the formula is the shortcut to solve the problem. You want it always to be very visible. You want to have an easy time finding it. I put the meaning of each symbol. I've done that in color here, right? The rate of change of momentum, and I highly recommend you use color too. It makes it really pleasant for the monkey brain. When you are looking at just black text on white paper for too long, it's so boring. It's so boring. And color helps you to see things easily and quickly. So get a color pin, use colors as you take notes online, however you do it. Totally recommend it though. So the rate of change of momentum, that's in orange. I put that in orange right here. In words, in math. Directly proportional to the symbol proportionality. I put it in words and math. F, the force applied on. This tells me specifically what these symbols are meaning in this context. And physics is always context dependent. We put the math here, F equals ma, is very short. It's a very simple seeming equation. But you got to know how to apply it in a plethora of different situations. And putting these words onto the page will really help you do that. And even months later after you've taken your physics course, still be able to utilize these skills. The uses for the formula are important. Record them in your notes. I can't tell. Imagine you've been doing physics for maybe 2 months now, and you've accumulated maybe 30, 40 equations, right? Formulas. And then you're going to go do your midterm, and you have to find out, he gives you a problem, and you have to find out which one of these you're going to use, right? It's very handy if you've recorded the uses of the different equations, and you can reference that. And you have that in your notes, you have that in your memory. So this is how I encourage you to take notes. We go to the next slide. Here's an example of how I first started taking notes. This is a bad example. So I've got some nice diagrams here. For me, this is pretty good. I'm not like great at drawing, so I'm pretty proud of these diagrams. I have no issues with those. But what's bad about this is it's a mess. There's equations everywhere. Nothing's boxed. Nothing's easy to find. I've just written out math, right? It's like I did the derivation. I found the formula, but where is it? It's just somewhere. It's just somewhere in the middle of this equation soup, I will call it. Equation soup. You never want that. You always want it easy to reference, easy to find. What else is bad about this? Where are my units? So I'm talking about static friction, and almost nowhere in here do I reference any units. So am I talking about meters? Am I talking about accelerations, forces? What am I talking about here? I need to put my units. That makes it very difficult to utilize later and cross-reference and check. This is how I take notes now. This was my notes from Physics 1C a couple of months ago. So what am I working on here? I'm working on alternating current. I wish it was a little bit bigger for you guys, a little more clear. I brought my notebooks in person, so if you were here, I could flip you through them one by one, and we can go through this. But hopefully you guys can kind of see. I'll cross over and talk about it a little bit. So this is alternating current. Don't worry about that. This is from electronics. Maybe you'll learn this. Maybe you don't need to learn this. Don't worry about the specifics. Just notice kind of the structure, the overall structure. So I've got the topic here. All the equations that I need to utilize, the key ones, the important ones, the useful ones, I've got in a box. And then next to that box, I write out what everything means. This may seem unnecessary when you're learning the class, but it's definitely going to help you a few weeks later when you're trying to remember what you were working on before. This saves my life every time. I've got students coming in to work on physics problems, and I flip through my book and I try to find the relevant equation, and I see P equals I squared R. And I think, oh man, what is I again? Well, I got it right here, right? I've got it right here. So do yourself a favor and put constant reminders. What are the units? What do the symbols mean? And a lot of times, letters will occur more than once, right? P, we already saw P used once as pressure. P right here, P means power. Sometimes you see P for momentum. Sometimes you see something that looks very much like a P. It's actually a rho, and it's for density. So make sure you write notes for yourself. What do the symbols mean? What do the symbols mean? That pretty much wraps it up. I'll turn it over to questions after a little bit of a summary. So the two takeaways that I would have for you guys as you're going through your physics courses, and I think honestly, if I were able to do this in the very beginning of my physics, it would have been much, much easier for me. So really, I would encourage you to utilize these methods, because really you're saving yourself a lot of work if you will go through them, all right? Interrogate your equations. Don't expect yourself to understand it in an instant. Give yourself 5 minutes if you need to read an equation. Take as much time as you need, right? What are the variables? How is it used? What are the implications? If I increase the power, what happens to the current? For any equation, always ask those questions. What are the units? On your note-taking, then stay organized. Make your equations easy to find and easy to reference. This was what I did terrible. That's like the big reason that I wanted to tell you guys all this. Maybe you're smarter brain than me. Maybe you weren't going to do this. But if you keep your equations in the mix of all the math that you work out in class, then when you need to find them and reference them to solve other problems, it's way hard. It's way too hard. And don't rely on the professor to give you a formula sheet. That's like a paper of someone else's work. It's supposed to tell you where to use the formulas, but it's the same problem of how do you read it. You have to be intimately familiar with it, and that comes with making your notes, writing the words, writing the math, and interrogating them. Express them in words as well as symbolically. Be explicit. Really spell it out for yourself, right? You're making a note to your future self so that when you go back and review in 3 weeks, you have a sentence telling you what it was that you were doing, what it was that this was about. If you can do those things, I think you'll be super well set up in your study of physics. I'll turn it over to you guys. If you have any questions, you can ask, maybe give yourself a little bit of a leg up. Remember, I'm a student just like you, so all the courses that you went through or that you're about to go through, I did. I'm transferring over to UCLA soon, so I think I've mostly got that cracked. I've got it figured out. Feel free to ask me any questions that you think would give you a leg up.
So, like outside of the textbook and your professors, whenever you're studying physics on your own, like, are there any other outside sources that you use to kind of help you get a better understanding of the topic? Like, for instance, a certain YouTube channel or a certain website?
Yeah, awesome question. So the first part is, do I use outside sources? The answer is absolutely. Whenever the professor's explanation didn't really work for me, right? Like I didn't get it. Plenty of times this happened. I would look for other explanations, right? Listen to other people explain the topic, and sometimes it just clicks. Specifically, I've always really loved Khan Academy. They've got some really great videos for the entry-level physics. So like your first, maybe your second physics course, they're going to have a lot of great videos for you. I always love Khan Academy. I think that's the number one that I use outside of a textbook.
So you mentioned
That was a great question. Does that answer your question?
Yeah.
Okay, super. Any other questions?
Also, kind of following up on that question, you said that Khan Academy was a great source for like the entry-level physics courses, right? So
Yeah.
as you get later on into the series of physics, like, and you get stuck, like, I guess how would you deal with that, or how do you try to find ways to help yourself?
That's another fantastic question. And you're exactly right. The further you go in college level physics, the less videos, the less extra materials there are online, and also the less friendly the material becomes. So there's a lot of really great YouTubers who do like really great explanations, really in-depth videos. But as you start to get into the more advanced topics, it's more scarce, and you'll often find yourself like, if you need help with a specific concept that's at a higher level, maybe you find like one forum where it's talked about, and you have to just read someone's post from a forum. So the resources can become slim. I would really recommend that you plug in to the tutoring center here at MathSci STEM Center. I've done well in my physics courses, and one of the main reasons is because I'm practicing on my own, and I'm also practicing with my fellow students, and I'm also working with tutors. You don't just get tutoring when you're struggling, right? You do it whenever there's just a little thing that you want to understand better. Do it all the time. Do it as much as you can, as much as you want to. What's also good is as you get into the more advanced levels, as the resources get a little bit tougher, you've developed a set of skills that also help you to tackle more difficult problems and to think about more difficult things. So you kind of grow into it. But I think, yeah, as long as you plug in and you ask other people, you talk with other people, you be very proactive in trying to make sure that you understand every little thing, every little thing. Little misunderstandings or little barriers that create confusion later on.
Also, another question is, when you're watching your lecture or when you're attending a lecture, is there like a specific thing that you focus on or that you want to get out of your lecture? For instance, like understanding the meaning of the formulas or knowing how to apply the formulas? Or do you just listen to the lecture and then just try to understand everything all at once?
So I think you nailed it with what you said initially. When I'm listening to a lecture and I'm presented with a formula, I'm trying to understand and be able to read the formula, and I'm trying to understand when it's applied and when it's useful, right? Because those are the two things, especially as a student. Like if I just wanted to eventually develop a very good understanding of physics, my main concern would be just my general understanding. But as a student, you want to do well in your courses. So make sure you know when to plug this stuff into your problems, how it can help you solve the problems that are going to be on your test. So I think it's good to have a dual mind, right? On the one hand, you're a student trying to learn as much as you can about physics. On the other hand, you're trying to think about what's going to be on the test, what am I going to be tested on, what kind of problems will I face, what will I use, how will I solve them. The combination of those two. I like to, in my lecture, take brief notes about all the formulas the same way that I was telling you, and then sometimes I clean them up afterwards and review them that way.
Yeah, that's all the questions that I have at the time being.
Super,
Thank you for
super. I'm going to
answering
go
that.
to the final slide here, which is just to say, enjoy studying physics. I hope you do enjoy it. I love physics so much. You can get caught up sometimes, like I said, in the woods, in the forest of math, right? It's just a bunch of black letters on white paper. And sometimes we forget what all physics is involved in and how powerful that it truly is. There's no piece of technology that you can utilize or pick up that doesn't operate on the basis of physical principles that we've discovered, right? Here we have the International Space Station. We've got the successor to Arecibo is a Chinese radio telescope. F-15, Hoover Dam, SpaceX Falcon Heavy, Apollo astronauts on the moon, skyscrapers, maglev trains, the CERN Super Collider, and an up-close photo of Mars. All of this is enabled by physics, and it's really, really a super fascinating, exciting, and very powerful subject. So whenever you find yourself too stuck in the math, just go watch a rocket launch on YouTube, or look what the astronauts are doing on the ISS, and remind yourself how great the things that we're able to accomplish with physics and with science actually are, and how exciting all that is. Okay, guys, thank you all so much. This has been great. So you have your worksheet. I encourage you to work through that. And I encourage you to maybe keep the worksheet or keep the slideshow and use that to kind of train yourself into those methods of interrogating your equations and taking clear notes. And if you can do that, you're going to be many, many steps ahead. You'll be very organized. You'll be ready to solve problems, and things are going to make sense to you. You won't be so confused.
All right, thank you so much for this workshop.
Yeah, thank you guys. So I'll be doing more workshops in the future. The future workshops are going to be more us practicing problems together actively. This one I wanted to just give you guys an idea of what I wish I knew when I was starting to study physics for the first time. That the professors don't really tell you. It's not, they're teaching you physics. They're not telling you how to be efficient as a student, right? But you've got other things going on in your life. You've got other classes. You want to learn as much as you can, but you want to do it as efficiently as possible. So I wanted to try to present you guys with how I tried to figure out how to do that over the course of the last year. In the future, we'll just practice more problems if you're here with me. And if you swing by the NatSci STEM Center whenever we've got tutors available, we love to work on problems and we love to help you. You don't even have to be struggling. You can just come talk to us, talk through your concepts. It's great for your active recall, and it will help you in your courses, even if you're not struggling. I can't encourage it enough. Okay, I'm going to sign off, guys, unless there's any last questions. Thank you. You've been fantastic. I hope to see you around in the future.